All right. Everybody have a good Thanksgiving break. Here's a fun use of computer science, computer programming stuff from yesterday. We've been having a problem with our grad program. So the master's in computer science here has almost 1,000 students in it. And we have many international students, and there's interesting rules you have to follow with student visas and things like that. So if you haven't noticed, on Mondays there's 1,000 Indian students here on campus. Those are those are our students. So I run a conference basically every Monday, but it gets very entertaining, and it's really an ingenious way of problem solving. But we've had to go through all sorts of different ways of taking attendance. We've installed a scanner. Well, so we're supposed to have roughly 1,000 people between the two sessions we have on Mondays. That just basically should fill the auditorium. Well, we obviously don't have anywhere near that many physical students in the room. Yet somehow we do have that many, well, close to that many IDs making it onto campus. So, I did like a head count. We had like 200 people total yesterday, yet we had over 900 people scan in. So a lot of these students are traveling from Chicago, so what I'm guessing they're doing is they're getting together as a group and they're deciding who's attending class this week, and they collect IDs that they can go and so I wrote some software that tried to process our attendance list to try to find patterns where like the same group of people were signing in and signing out within like the same 30 seconds of each other. So it was kind of a fun, I guess, software thing. So I was able to identify here. You can even see the output of some of it over here. These are all groups of like packs of students. This is 12 students that were part of some group of people who signed in and signed out at within 30 seconds of each other both times. They signed in within 30 seconds of each other, the same group of food numbers, and signed out the same group of food numbers. It's really actually kind of amazing. The lengths that these students will go to bypass it. At the end of the day, I don't necessarily care, but also at the end of the day, the government asked me to give them an attendance sheet, and ethically, I should probably give them accurate attendance because that's the agreement Concordia made with the government. But I don't know, just a fun computer science problem solving type thing. All right. Did we have homework over break? Oh, homework. That doesn't seem right. Did you miss it?
You're not having
I thought I was dreaming. All right. Oh, another interesting thing I can show you real quick. That yesterday's lecture to the I give the quantum computing lectures, and we covered this famous algorithm, and it's related to what we've been doing in here. Looking at these different time complexity problems and how sometimes we'll run into issues. So there's a famous algorithm called Grover's algorithm. So it's another one of the famous quantum algorithms from the 1990s is when he came up with this thing. And but it's for solves problems related to optimization. So we had talked previously about Shor's algorithm allows you to crack like RSA much quicker and that kind of stuff. Well, Grover's algorithm, I think, is kind of maybe more compatible with normal computer science students, because all of you are going to be doing something with quantum computing in your careers, as well as AI, as well as virtual reality. These things are all going to intermix regardless of what your job ends up being. But Grover's algorithm is kind of more understandable for a current computer programmer mindset, because there's a part of it that you can apply to different kinds of problems. So the example we used in class, how many of you have ever done the Where's Waldo things? You know what I'm talking about? Where you got the giant screen. It's like, okay, can anybody find Waldo in that picture? Oh, you found him that quick? You're like a savant. Where? Yeah, he is. Yeah, so he's right there. So there's Waldo. Man, was that just luck?
I don't know. I mean, being in the top right,
Oh, I see. So, but in any case, so we have this issue. So the normal human approach would be what? We would look, all of us in our ability, we can say, we can look at a person and say, is that Waldo or is that not Waldo? Right? So what would our human approach be? Is we'd look at each individual person in the picture. Are you Waldo? No. Are you Waldo? No. Are you Waldo? No. And we'd have to do it, whatever, 300 times, however many people are in this picture. So we use the example of who betrayed Jesus from the apostles. And what's extra interesting about this is a majority of this audience are non-Christians. And there's a lot of Muslims in the audience. From a Concordia mission perspective, it's kind of a cool thing that we get to kind of share that stuff with that audience. So we picked this as the storyline. So we're gonna use Grover's algorithm to discover who betrayed Jesus, is the example. And I'll go through this reasonably quickly. I won't spend an hour on this or anything on it, but just to give you an idea of a quantum algorithm, it's a little bit more understandable. So we initially have our list of suspects, right? So these are the possible suspects. And then we bring in, so in Grover's algorithm, he has this component called the oracle. Okay, so just like I said, all of us in here, we if we put somebody in front of us, we can determine, is that Waldo or is that not Waldo? The oracle in this particular problem is one of the Pharisees. So this guy, he knows, is this the one who betrayed Jesus or is he not the one that betrayed Jesus? Okay, that type of thing. This is Bob the Pharisee, by the way. that's where he came from. But this also gives us a kind of a cleaner way of kind of talking about where's the power of quantum. So you think about your 4 lectures you had in here dealing with quantum computing, and it's really heady stuff, and it's kind of hard to wrap your mind around like, where does quantum actually help us? What problems will we actually use quantum computing for? That kind of stuff. Well, this is a problem that really shows you the power of it. And this is true among any quantum algorithm. So one of the things I like to do when I'm teaching on quantum stuff is looking at famous existing algorithms, and traditional computer scientists can start seeing patterns in those. Like, oh, it seems like all 5 of these algorithms all do the same kind of little thing, or they all do this, they all do that. Well, at the center of all quantum algorithms is our idea of the quantum oracle. And what that means is, if we brought in Bob the Pharisee here and had him, try to help us identify who was the betrayer, he would walk up to each individual apostle, right? And, give a thumbs up or a thumbs down, whatever. But in the quantum world, Bob can deal with all of them at the same time. That's the magic of quantum, is that one fact, is that no matter how many states you have, in this case, we have 12 apostles, but in this state, we might have, 300 people who are possible suspects. So if you are the oracle in this case, you don't have to go up to each of the 300 people. Instead, you can go up to all 300 people all at the same time in parallel. That's where quantum becomes awesome, is that you can do those kinds of things in extreme parallel. So we bring in Bob the Pharisee, and what he does is he interacts with all of the apostles at the same time, and he's going to mark the one that is the bad guy. All right. So we see we look at the little first place ribbon here, And the reality is we're getting kind of a sneak peek into the state of the qubits here, because as soon as you observe a qubit, it collapses. You no longer have this stuff. So we're actually breaking the laws of physics here by allowing us to see what's going on. But so the Pharisee has done something to this qubit. We have a qubit representing each of these guys. So he's done something to this qubit. It's called a phase flip, but he hasn't done anything to the other ones. And then we have another pass come in that I've represented as a wizard. And what the wizard does is he does something to these guys where he exaggerates the ones that were marked and depresses the ones that were not. So already at a glance, you're starting to see one of these guys standing out, right? Then we go and do it again. We do it again, do it again, do it again. So now all of a sudden, so what we've done is we've gone through this quantum process, in this case, 3 times. Grover's algorithm has what's called quadratic increase in the speed. So we're decreasing the number. If we have the human version of scanning Where's Waldo, except for this guy, is we might have to deal with 300 people if there's 300 possible people that could be Waldo, right? So the best chance is we get Waldo the very first person we interview, like him. Worst thing is we have to look at all 300, and Waldo's the 300th person. On average, it's 150, right? We're gonna have to look at out of those 300. So we call that order n. So that we have this thing in computer science efficiency stuff called big O notation. Whereas Grover's algorithm speeds that up, where our average number of checks is the square root of that. That's called quadratic speed improvement. So not quite as good as Shor's algorithm, which is exponential, where we turn 3 trillion years into like an hour. That's pretty cool. So that's the poster boy for quantum. But Grover's algorithm is much more practical for solving all sorts of problems, because we can just reprogram that oracle, that one piece, and now it can solve a different problem. All of you were able to play the role of the oracle from the perspective of being able to identify Waldo. We brought in this Bob the Pharisee because he was there. He was an eyewitness for the guy who betrayed Jesus, so he could point him out. All right, but he doesn't operate as, like, oh, he's that guy over there. What he does is he goes and marks the qubit, does something to the qubit, and we do that over and over and over again until the states of these 12 qubits might look like this. If we were able to peek inside them, they look like this, where one of these states being highly, highly exaggerated, with the final idea that when we then go to measure the quantum circuit, so we measure our 12 qubits, we end up getting something that looks like this, where we have one of our 12 states really sticking out with a high probability of being the answer, where all the other ones are very depressed. Now, that doesn't mean that we might not accidentally accuse Simon if we rolled the dice and we happen to get a 1 on him instead of a 0, but we've set it up in such a way where there's an extremely high % chance that we get zeros in all these positions, and we get a 1 in this position, then we know who the guilty party is. And then I got to this slide. It didn't play on the thing in the auditorium. Is it playing here? See, I have the Bad Boys thing. No, not playing. Maybe it's just, that's the Cops theme song, bad boys, what you gonna do? So in any case, that's an example of a famous quantum algorithm. But what's exciting about that for computer scientists that are normal programmers is this idea of that oracle, where we can take that Grover's algorithm and not change anything except the oracle. That the oracle knows how to solve a different problem. Instead of identifying the betrayer, or instead of identifying Waldo, we can use it for self-driving, identifying stop signs, for example, stuff like that. So we can think of the oracle like an if statement. It gives us a true or false, and the only thing we can't change is how the oracle marks the state that is or multiple states. It can work for multiple states as well. So we can't change that, but from a computer programmer perspective, we can use this exact algorithm for all sorts of different problems. All we have to do is change the if statement that the oracle represents. So kind of a cool use of quantum that will be among our first practical uses of quantum when we have actual quantum computers with enough qubits that it allows us to solve these problems. We already have quantum computers with more than 12 qubits, so we can solve the apostle issue. This one we can actually represent on the quantum computer, but realistically bringing that Bob the Pharisee in and talking to each of the 12 apostles individually wouldn't have taken that long. So I'm not sure we haul the quantum computer in for that, but you could. So kind of an interesting thing, but we don't quite have, actually we do now. We probably do have a quantum computer from IBM that's capable of solving the Waldo problem for this particular one. It only has, well, let's guess that's 300 people. Kind of a fun example, I guess, I think so, but perhaps I'm biased. All right, so back to the non-quantum world. All right. Anything else? Was this over break that the OpenAI Q-star thing came out? Is that over break? Did we already talk about that? I think when we had discussed the whole thing going on with OpenAI before break, and one of the conspiracy theories was that inside of one of the reasons why they forced Sam Altman out or whatever may have been that inside of OpenAI they had made a breakthrough in something called general intelligence. Well, it turned out that there was truth to that. So there's a model that they have inside of OpenAI, and to the average person, I mean, we don't have that much information about it. It might not actually seem like such a big breakthrough, but the math behind it and the difference it has from our general models like ChatGPT is, inside of OpenAI, they call general intelligence a model that's smarter than a human. And apparently they have something that's showing some promise towards that, where you're going to now have the robots running around and taking over, and it'll be awesome. So at least we'll have probably robot cab drivers first. So rather than teach the cars to drive themselves, we'll just have a robot driving the car.
I make a phone conversation with them.
That's true. All right. So we had looked at the idea of static versus non-static methods. So just to kind of roll back here a couple of slides to bring us back into reality. We started talking about security on the fields within our classes, with this idea that we had kind of a rule of thumb: make things private first and then loosen the reins if you have to. And we kind of saw the reason for that is if you have your fields, which are the variables owned by your instances of your objects, if you have those fields existing as public, that means anybody outside of that class could directly change the value of your fields rather than having to go through like an intermediary, like we call them getters and setters. All right, so we probably want to have all of our fields as private. And then if we need external entities to be able to read the value from a field, we can give them read-only access through a getter. Just a function usually called like get, whatever the name of the field is, and it just returns the value. It does not let you change the value, doesn't let you update it, just gives it to you. So we can make something private and then allow read-only access to it. Some of the more modern languages do have property security things built into it, which will kind of automatically generate getters and setters for you if you want to make it read-only, or you want to make it write-only or read-write. You can do that at the time you're defining the fields, but at the end of the day, it's just syntactic sugar for something we can write ourselves. And these getters and setters are typically not, I mean, they're like three-line methods, right? Get age, return this dot age. That's the whole function. So we talked about the security stuff. We talked about our getters and setters. They used to be called mutators and accessors. This is just a generic name for these types of things. These are just normal functions that either return a value of one of your private fields, or might let you set the value possibly with some oversight. Maybe you have an if statement, you don't let them set a numerator to something less than or equal to 0, perhaps. Then you start getting into imaginary numbers and that kind of stuff. So you can do that for your fractions if you want to let them, an external entity, update your denominator, for example. Then we started talking about static versus non-static members, and we looked at this through an example with our fraction classes. And let me actually pop that open here while we're talking about it. Who do I log in as here? Do I log in as my GitHub? Oh, perfect. This is my fraction stuff. No, that's from 2021. That's old fraction stuff. The good news is we're getting ready to start working on our dungeon crawler. And that's awesome. We're going to write Dungeons and Dragons in here. All right, so let me log out. Let's go with maybe my Google sign in. Yeah, this is it. I'm just showing you what not to do. Probably don't use 11 different accounts on the same site. And depending on what was logged in at the time, you just go with that for half a semester until you've restarted your computer, cleared the cookies, or updated the OS, and you get logged out. Then you forgot what you logged in as, and you log back in as a different person. Add that up over multiple years, and you get this situation. All right. What I should do is start putting little funny project names in here as like Easter eggs and see when they when it pops up. Let's see. Was it in our, we've been working on it in our homework thing. Yeah, this guy looks, he looks right. Okay, so we'll go into our fraction HPP. Okay, now I remember. I think at the end of class we had a little bug. I said I was going to fix it afterwards, so I left you with code that was working. But in any case here, so here's our fraction class. We have our header file. Our header file gives us kind of our summary of what's available here. So we have our private section. Private section, we have 2 private fields, numerator and a denominator, which means we can only access those guys inside of a class name fraction. We won't be able to do it out in main directly. We'll have to indirectly do it through our functions. I'm going to come back to this here in a second. Then we have our public functions here. We have our constructor that gets used along with a new keyword for generating new instances of fractions, where an instance of a fraction gets a copy of all the non-static things. So every fraction has a numerator. Every fraction has their own denominator. Every fraction has their own display method, has their own add method, has their own reduce method. And those methods, they know about the numerator and the denominator of that particular fraction. Okay, so non-static stuff is individualized for instances of an object. All right, that kind of makes sense. So basically up to this point, everything we've really messed with is non-static. Now we start throwing in the idea of these static functions. So static functions or static members of a class. What are the 3 members of any class? So if I asked you on an exam, maybe for a class in C++, what are the 3 members that make up all classes? I maybe have them listed as comments on the current screen. Number 1 is fields, right? These are the variables associated with the class. Number 2, I have methods on there twice because I have 2 different style methods, let's say. So number 2, we can say constructors. All classes have 1 or more constructors. it actually is possible for you to not write any constructors, and one will be provided for you that takes in no parameters and just is used with the new keyword. So if you don't actually have any real initialization to do in your objects, you don't actually have to write a constructor. You will get one if you don't. But if you do write a constructor, like in this case, we wrote a constructor that takes the numerator and the denominator in, a no argument constructor will not be given to us. So you won't get that other free constructor unless you don't write one. All right. Good rule of thumb is always write a constructor. Even if you're not going to do anything in there, sometimes just having the ability to interject something into your code at the moment when something is being instantiated can be helpful. You know, when you're debugging something and you want to just print something out saying, you know, hi, I'm fraction 1/2 and I'm fraction 3/4, you know, whatever it is. All right. And then the third thing that makes up all classes are set of methods. All right. So a class could have 0 or more fields. It could have 1 or more constructors, and it can have 0 or more methods. The closer to 0 you have on all those things, the less interesting your class is likely to be. Okay. Now, with that in mind, notice here that we have added one method here. And I put it in the private sector, so don't confuse the static keyword along with private and public. They're unrelated, they're indirectly related. So in this case, something being static means it only exists one time. I've put it inside the fraction class, even though you probably could make an argument that GCD, that's the Euclidean algorithm we talked about, greatest common divisor, that's more of kind of just like a high level math thing. So you maybe would have a math library, and inside that you'd have GCD, where whenever you needed the greatest common divisor of 2 numbers, you would just say math.gcd because that's where it lives. But we only need the Euclidean algorithm to exist one time. Every single copy of fraction does not need to get its own copy of GCD. It didn't hurt anything when we did that, right? Just used up some more memory. So really, we're talking about, you know, optimization of this, which is Grover's algorithm. Click, we connected them. Perfect. Connected quantum to that stuff. But if we're talking about best practices in computer programming, we're going to say, look, every single instance of fraction does not need to have their own version of Euclidean algorithm, because the values associated with GCD are not directly related to the numerator and denominator of a particular fraction. Make sense? So what we did, we said, okay, well, we're going to make this guy a static method then, which means it exists exactly one time. All right. No matter how many fractions we create, it happens one time. And the way we access that guy, let me hide this. The way we access that guy, well, notice here I wrote it. This is me writing it. So notice for these guys up here, whenever I wrote the constructor, or I wrote like reduce, I connected it with my class using this fraction. This is the scope operator, I guess we'd call it, to connect it to a namespace or a header file in this case. So we connect it back to the header file using this little syntax here. We do the same thing with GCD because that's where we defined this guy. But notice that we did not include the keyword static out here. So we only know that this guy was implemented as a static function when we're looking in the header file here. So this tells us how we should use it in the wild. So this is even more evidence maybe towards header files making decent sense, because this guy really gives us the schematic of how fractions work in our implementation. And so as we're looking at this, I say, oh, do I want to use GCD? Yes, I notice it's static. I also notice it's private. Private means I can only access it if I'm inside the fraction class. It's unrelated to static or not static. Static means it only exists once. So if I want to call it, which we would be doing in our reduce function. So here's reduce. Notice I'm not calling it with an instance of the fraction. I'm calling it with the fraction class itself. All right, that makes sense. So it doesn't matter whose reduced method I'm in, whether it's fraction F1, F2, F3, F4, inside of there, we are calling the single GCD function owned by the fraction class. You know, it's up on the mountain somewhere. All right, we could think of this as a factory. We have a greatest common divisor factory that this particular fraction will throw his numerator and his denominator at. This guy will return for us the greatest common divisor of those two, and then we'll update the numerator and denominator appropriately. Makes some sense? So there's a rationale for why we may want some methods to be static. Okay? But again, we saw you could just make it an instance method and we'll just have the Euclidean algorithm floating all over the place. And it would just change the way we called it here. Technically, if we have 5 fractions, we have 5 copies of the Euclidean algorithm. Today's world, probably not hurting anything, but you can imagine as the problem gets bigger and this kind of stuff, using best practices makes more sense. Things could get out of control pretty quickly. All right, so questions about static versus non-static in general. This is similar to the this keyword. Static versus non-static is it traditionally has been a difficult concept for students to grasp. And it's a super, super important concept. It's kind of like one of those top 5 guys, because understanding that allows you to read documentation. And being able to read documentation and immediately use those tools correctly is powerful. All right. You know, like I've said in class, I think several times, you know, I've been programming since I was 9. What percent of, let's take Java as an example. So I've been programming Java since it came out. All right. I was older than 9 then, but you know, since Java came out, I've been writing Java code. What percent of that programming language do you think I've memorized? Not very much of it, right? I mean, there's common stuff that you use all the time that I've memorized. And we've seen in this class that some of those things travel through the history of our languages, C and C++ and Java and C#, all the uses, you know, for loops look the same, if statements look the same, all these things travel through. But in terms of, if you look at the documentation of Java, there's something like, there's hundreds of classes built into Java dealing with all sorts of different problems that might be completely foreign to me, things that I've never actually had to solve with, right? So nobody on the planet has memorized the entire Java language. I hope that's true. It's possible you run into some Waldo guy like him that we have the remake. I wonder why they haven't done that, because we remake all the other movies. Why haven't we remade Rain Man? We bring you in as the Waldo guy. On your resume, you know, it's like 18 years of experience in quotes, Waldo guy. Actually, probably would come up in every interview, would be a good icebreaker. I think that would be a positive thing to do from getting a job perspective. Test it and let us know. I don't even think it would go that far. I think it would just be one of those things that comes up in the interview. Like, tell us about the Waldo guy thing, and then immediately kind of de-stresses the interview process and makes you likable right from the get-go or whatever. It's a pretty good strategy, actually. It's the equivalent of when he's pitching, he throws at the first batter's head. That makes all the other batters be wary that this guy might be wild. That's his go-to move. All right. So I don't know how we got down that path, but we go down that stuff. That's a Lippmann thing, I guess. So in any case, we've made GCD static, and understanding how to use that is an important skill set for unlocking the documentation of any programming language. All right. And that is a super, super, super important skill, because I'm using the example here of I've been writing Java since the day it came out, yet I probably have seen less than 20% of the language in terms of ever having to use some of the classes. And I've probably memorized, I don't know, let's call it less than 5% of the language, just pulling numbers out of the sky. But a majority of the things built into the Java or directly accessible by Java, I don't have memorized. Yet I can use any of those things just by going to the Java documentation. So for example, if we go to Java, this would be a good example. So we'll do Java string. So I'm kind of going forward a little bit since we're going to be looking at Java-esque stuff at some point. So here's our string class in Java. Notice that we have a section for fields. We have a section for constructors. Notice there's a whole bunch of different ways we can build strings. So you're not stuck with a single constructor. You can have different ways of building strings. And then we have a whole collection of methods. All right, so each of these methods does different things, whatever. You can look at those directly. But really, from a documentation perspective, let me open up a separate thing. We're going to say Java character. And I'm purposely picking this character class because it's filled up with static stuff. So let's just go down to the methods, even though all the fields are static as well. So here's our method summary for the character class in Java. Notice that most of these guys are static methods. So in Java, the character class has a whole bunch of methods that are owned by the class, not instances of the class, for doing things to characters. And if you know how to read the documentation, and we see that, oh, I'm in the class called character, and I have, let's see, let's look at like 2 uppercase. That's a non-weird one. Better remember my ABCs. Okay, here's 2 uppercase. All right, and I'm going to also bring up 2 uppercase and strings, so we can kind of look at those right next to each other. So here's the 2 uppercase and strings. So notice here in a string, what would you guess that 2 uppercase does to a string? Probably gives you the uppercase version of it, right? All right, so not a trick question, but I want you to pay attention to an interesting thing here. Don't even look at the left side yet. 2 uppercase is the name of the method here, right? How many parameters does this take? 0, right? Here's the 2 uppercase for a character. How many parameters does that take? 1. Now, this behavior is not a guaranteed behavior between static and non-static methods, but it is a good way of explaining these two since they are effectively accomplishing the same thing. Go back to string here. Notice this guy is not static, which means every single instance of the string class gets its own copy of 2 uppercase. Make sense? Why doesn't 2 uppercase need to take a parameter in the string class? Why would you guess? You don't even need to guess. You can apply your direct knowledge from our fractions to this. Why doesn't 2 uppercase inside of string need any inputs? Go ahead. What's everything? So since this is an instance method, a non-static method, it already knows about the value this string holds. He internally knows about that, just like our fractions. Each instance of our fraction knows about its own numerator and denominator. Every single instance of a string knows the characters that it holds, the collection of characters that it holds. So when we tell a string to convert itself to uppercase, we don't need to give it anything extra. It knows the value it's going to operate on. It's the value that guy internally holds. Make some sense? Now, on the flip side, the character version of 2 uppercase is a static method. And what would you guess this does? Probably converts a character to uppercase. But because it's static, it's owned by the character class, not a particular instance of the character class. So when I call it, we'll talk about how to call it in a second because we're still reviewing our stuff from last time, but we're seeing a real life example of it. You know, when I do call this, I am calling the single version of this method. Therefore, the two uppercase method that's owned by the character class, not individual instances of the character class, but the class itself, it does not actually know about any internal value that you might be wanting it to convert to uppercase. You have to provide it with that value. Make sense? Okay, so you have like a little machine sitting over here that you could walk up to and you can toss any char into that machine and it'll pop out the uppercase version of that guy for you. The uppercase character toaster thing. Make sense? Whereas if we had three strings here, each one of them sitting in front of it would have a machine called two uppercase that you wouldn't have to put anything into. You would just walk up and hit the button and it would pop out the uppercase version of whatever string that particular string held. Make some sense? All right, so that gives you some differences between, in this case, why we might have the two uppercase method in the character class taking a parameter versus the string not needing a parameter. Okay? And don't necessarily think of this as, oh, it's going to be, if I see no parameters, that must mean it's a instance method, or because you could certainly have a static method, say, that says print woot, that doesn't actually need any inputs for it to print the word woot to the screen, right? So we could say fraction.print woot for no good reason, but we could do it, right? And that guy doesn't need any inputs from us in order to accomplish its task. But generally speaking, class methods, static methods, we're likely going to have to give them some information on which we want them to operate because they don't have an internal state that they can work with. Make some sense? All right. Whereas at the very least, instance methods, non-static methods, we at the very least won't have to provide it with information regarding the internal state it already has. We might have to give it some extra stuff. So like as an example, we have a substring method here. So in the substring method, which is also an instance method, it's non-static. The substring method already knows about the internal state of this string. It knows that the string holds hello world, for example. But substring gives you a portion of the string that string holds. So he is going to need a little bit of extra information from us so he knows where to start on the internal string to provide you with the rest of it from that beginning index. That makes some sense? There's a second version of substring here that takes a beginning and an ending index. So one version says, okay, you want everything from bucket 5 on? Gotcha. That's the first one. Second one, you want everything from bucket 5 to bucket 9? You can pass that range and it'll give you the stuff in between. Make some sense? All right, so these are like real uses of why you might have some things be static versus some things being non-static. One's not better or worse than the other. It's what's the right tool for the job. All right. So questions about that before I ask you a trick question. Well, not a trick question, but a question that you have enough information to answer, but it might be a hard question. Why is the character class here filled up predominantly with static methods? And if you want, you can think of this as being a C++. The answer would be the same whether we're dealing with Java or C++. So if we were looking at the C++ documentation here and looking at strings versus characters, why might the character methods all be class methods instead of instance methods? Why did they make that decision? We've already seen in our own code, because we wrote ours, that GCD was originally a non-static method, right? Where every fraction got its own copy of that guy. And then we decided, you know what? The method always does the same thing. Maybe we should just make it kind of a global method owned by all fractions. So it only exists once, and then we'll just internally use it. So we decided to make it static. But we could have made it work the other way. We did make it work the other way. So why do you think they decided for the character class that all of these methods should be static? Any guesses? The Waldo guy immediately noticed there's a picture of me on the mug. Didn't you? That's from the old competitive eating days. It's a whole nother story. So if Java is the same as C++ in many ways, which it is, because both of them are C-based languages, right? If you remember back to like week 1 of class when we had the hierarchy of the history of languages, you know, we had C and then C++, and then we had Java and then C# over to the side. So, you know, these guys are, let's call it evolutions of the C programming language. So what kinds of values does the character class operate on here? It operates on chars, right? What's a char? Tell me everything you know about a char in C++. So if somebody on an exam asked you to tell me everything you know about a char in C++, what might you say? What is a char? I'll get us started. One way or another, it holds a representation of a single character. Okay? How does it hold that representation, though? Remember back to our slide for primitive types, where we had byte, short, int, long, char. I purposely put those guys next to each other, right? Byte, short, int, long, those guys are all signed whole numbers. A byte is 8 bits, a short is 16 bits, a blah, 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 an int is 32 bits, and a long is 64 bits, but it's signed. That means built into those bits, we're having to keep track of the positive or negativeness of the number. But then when we got down to char, remember what char is? It's an unsigned value. In C++, how big is the value? Anybody remember? And the follow-up is, why is it that size? Why is it unsigned? Let's start with that. So in C++ and Java, it's an unsigned value. It's an unsigned integer, actually. And in C++, it's a 8-bit unsigned integer. In Java, it's a 16-bit unsigned integer. Well, computers like numbers. We've talked about that, right? So almost always, at some level inside the computer, the value is going to be represented as a number. In C++ days, we had a character mapping group called ASCII, American Standard Code for Information Interchange. All right, so ASCII had room, since there's 8 bits, for 256 unique characters. All right, so the number that we held inside of a char data type in C++ was some number between 0 and 255. And that number corresponded to one of the characters on that. It could be an A, it could be a B, it could be a question mark. Make sense? Java, a little bit newer language. We actually realized that, you know what, there are more languages on the earth than just English. So now they have 16 bits. So there's 65,536 unique characters that could be represented in the Java version of a char. Still an unsigned number. Now, could they have made chars signed? What if it was so if we think about C++, where the reality is that a char in C++ is stored as a 8-bit unsigned value. Could we have made it a signed value and still accomplish the exact same thing? How many unique ways can I write an 8-bit unsigned number? It's 2 to the 8th power. It's 256 unique ways. How many unique ways can I write a 8-bit unsigned, or I'm sorry, an 8-bit signed number? Still 2 to the 8th power, 256 unique ways. The difference is that an 8-bit unsigned number holds the values between 0 and 255. An 8-bit signed number holds the values -128 to +127. Still 256 unique values. So there's not a great reason other than just weirdness that we would have to, that we couldn't have chars represented as signed values. But then when you looked at the ASCII character set, you would see that, oh, character -73 is this guy. Character -38 is this guy. Character 14 is this guy. As opposed to all of your characters mapping to positive numbers. Make some sense? Because in this case, when we're dealing with chars, we're not actually using the numbers for math. You can actually do math with them. It's just that's not the purpose, right? We're using them as like placeholders, as numeric representations for a different meaning. Make some sense? So really nothing keeps us from using a signed number for it. It just would look weird if somebody gave you a lookup table and it started off with -127 and ended at, or -128 and ended at +127, and asked you, okay, well, what is the numeric representation of the question mark? And it might be a negative number, perhaps. You get what I'm saying? All right. So, in fact, in our for the English alphabet, because of where they are in the ASCII character set, all of them would be negative numbers. Would be the representation for all of them would be negative numbers, which would just seem weird, right? It's fine, you can do it. It's just weird. So they just decided, okay, we have 256 characters in ASCII. They're numbered 0 to 255. We need to store the numbers 0 to 255. How can we do that? In an unsigned char, unsigned integer. Make some sense why they chose that? Okay. In Java, basically the identical argument, except they use a different lookup table. Anybody know the name of the lookup table Java uses? We talked about it, but anybody remember the lookup table that Java uses? You don't go home every single night and just memorize every single word that comes out of your professor's mouth in every single one of your classes. I'm afraid not. It's called Unicode. It is that guy. Believe me, I remember a whole lot more stuff about my computer science education than I remember about my English and psychology classes and stuff like that. So I still encourage the computer science majors in here to focus heavily on their CS stuff, but I understand your pain of not having room for everything in there. And I think if some of you maybe heard me say it before, if I've said it in class, by far the hardest degree I did was the bachelor's degree by huge margins, because you're taking all these classes you're not interested in, right? Not that I think that's necessarily a bad thing. I do think it's a bad thing, but I understand the value in having a broad knowledge base, but I don't know. I feel like if you're going to be a computer scientist, it'd be best to have a whole bunch of computer science and maybe leave the psychology stuff to the psychologists or something like that. But I can understand the argument on the other side too. 15 credits of CCUs there. I actually have probably a more positive opinion of that at Concordia, though, because one of our things that are special sauce, if you will, is integrating a Christian worldview into the classroom. And I think those classes give us a very focused opportunity to do some of that stuff. I'm not sure they always accomplish it, but so I agree with those classes at a place like Concordia. I'm not sure you need to pay for a credit in bowling. It is, yeah, and it's been like that for years. I mean, when I was in school, we had the same stuff. The real irony, though, is if you're a student athlete, you can get out of the HHP classes, right? Including esports players. Hey, it's a varsity sport here. When I'm guessing if you statistically took it, it's possible that might be a group of people that could use a couple of extra steps, right? But it's actually not true. I mean, or not false. If you remember, after class last Tuesday, right before break, I had my next back surgery. So I had a back surgery last week, and I was supposed to go and, because it was a nerve block thing, so I was supposed to test to see if wherever they block stuff, it helped me. So I played 36 holes of golf because I'm a very avid golfer. Well, it was cold outside, so I did that all in VR. I have like a special golf club thing that I use that your controller hooks into. Yeah, so yeah, you don't need to leave the house for this crap. What was I talking about? Let's see, how do we get onto that subject? We were talking about Unicode and memorizing everything that ever comes out of all of your professors' mouths. So do that better. All right. So in any case, newer language like Java decided, hey, there are people all over the world that speak different languages. It might be nice for us to have a character set that incorporates some of the characters from other languages into it, especially when you go back and look at ASCII. And it really, you know, spits in your face because ASCII actually doesn't use all 256 spots. It uses some a little bit less than 127, and then the rest of them, if you look at it, has like smiley faces and like playing cards and stuff. Because remember, this is old, so you know, like the idea of making a poker game on a text-based, you know, screen. So some of it makes sense, but I mean, they didn't even use the extra space for other languages then. They have 11 different smiley faces. The precursor to the emojis. Very sad. All right. So what we wanted to get out of all of that is just kind of the rationale, the people that were designing these languages, what rationale they went through to decide is something going to be static or is it going to be non-static, and some of these other decisions as well. Make sense? And why that's important is A, you want to see that there was some rationalization around it, but also B, really pushing this agenda that the ability to read documentation is absolutely critical as a software developer. I promise you, when you go out into industry, you are going to be having to use tools and using languages that you didn't learn in school. They all have a basis in those, just like I'm telling you that Java is basically C++ with some fine tuning. C# is basically Java with not very much fine tuning, but we'll give it a little bit. But these guys are all kind of the same ideas, but having these tools in our tool belt so that we can go and look at the documentation for a language that we just were introduced to and be able to immediately use it, I think is very powerful. And that even goes back to one of our early slides about how do human beings solve problems: memory, asking questions, repetition. And me saying that 100% of programming languages have facilities for these three things. So if I showed you a brand new language today and I showed you, how do you remember stuff? How do you define variables? How do you ask questions? How do you write an if statement? And how do you represent repetition? maybe writing loops and writing functions, you can already solve a whole bunch of problems in that language day one. And then when you start bringing in some of the power tools that are built into that language, that's when your ability to read the documentation and the consistency of some of these terms across object-oriented languages, like the static keyword that exists in C++, it exists in Java, it exists in C#, it exists in Swift, it exists in Objective-C, that word's there, all right? The this keyword, it exists in all those languages with some of them call it self, but generally that concept exists in all those languages. Public, private, protected exists in all of those languages. All object-oriented languages have security settings for their fields and their methods. All right, makes some sense? So these things all have rationalizations, and you will be able to leverage your knowledge base much better having a strong understanding of those fundamental concepts so that you can quickly get to the stuff you need to use in a language where you haven't used their tool set before, as opposed to thinking that you're going to be able to memorize everything you're ever going to need to do, because you won't. All right. So go back to our code. I'm already on this guy. All right, so that was our rationale why we made GCD static. We only needed it to exist once. We decided it should belong to the fraction class in our little world. We certainly could have made our own math class and just thrown it in there. And then when we called it, we would have said math : GCD. But having these things is an important piece. In fact, let me actually go down. Well, do I want to introduce it in this? No, I want to introduce it in our dungeon crawler. All right. So any questions about our fraction stuff before we jump into our next project we're going to build on really probably through the rest of the semester? All right. So let me show you how many of you have ever heard of a type of computer game known as a MUD, a multi-user dungeon? Anybody heard of that before? Something that looks like this. Make that bigger. Is that what all your video games look like that you play? So you don't remember this, but there used to be a time when we didn't have $1,000 graphics cards that could push zillions and zillions and zillions of pixels on the screen at once and represent zillions of triangles with floating point math for actually creating all of these cool, fancy graphics and things like that. But those have not been around forever. So yet, do you think that day one, when consumers started using computers, there was some subset of those consumers that wanted to come up with video games for them? That's what people do, right? Yeah, what can we do for fun, right? So in the early days, notice here that they're using all sorts of different symbols to have like fake graphics in here, right? There are some old programs like this that actually have color and stuff, and they're using another character set called ANSI, ANSI, for actually getting colors and things like that on the non-Windowsy, non-Mac OS type of operating systems. We were still all text-based operating systems, but we had color monitors. We haven't always had color monitors. Once upon a time, we had monitors where all the text was orange. Yeah, back in the cathode ray tube time, CRTs, but in the early days of that, they filled the tube with the different kind of gas that made it show up as orange. I think it was a really bad idea to break those though, because whatever it had was in there, I think was extra bad for you. But So that's why they're not orange anymore. They went to non-orange ones. But in any case, so we had this type of game called a MUD, a multi-user dungeon. And really what these guys are, they're trying to take the idea of Dungeons and Dragons. Everybody's heard of that phrase before, right? All right, so I'm guessing, have any of you ever actually played old school tabletop Dungeons and Dragons? Oh, a couple people. It was kind of at a, it's almost like at a reenactment fair where you go to every year people have like reenactments of like the fight at Lexington and Concord. It's like, oh yeah, we were reenacting early day video games. But in any case, you and your friends used to gather around this table, and one of them was the dungeon master, right? And he would sometimes he'd have a little map he drew out on paper or something like that, or maybe today's version we might use sweet and low packets or something like that to build our walls and things like that. I mean, we've all done that, right? Have you ever tried to explain a concept using the fake sugar packets on the table at the restaurant? All right, so we're just representing stuff, right? So that's how human beings solve problems. So they would come up with some sort of representation of what's going on. They'd have the 2 or 3 or 4 friends sitting across the table, and the dungeon master would play as all the bad guys. Okay, and then you have your heroes that are sitting at the table, and they would say, they would say, okay, well, we're going to go down the wooded path. And you say, okay, well, you've come upon a group of orcs. And they catch you by surprise, and then everybody has dice, and you roll for initiative, and you start this fight, and you decide, okay, well, I'm going to attack this guy, and then I'm going to move over here, stuff like that. All right, super, I mean, epic. We used to have epic battles. 4 a.m, a bunch of nerds around a table in my basement. True story. All right. So anyways, in the early days of computers, they decided, hey, let's try to turn that into a game on a computer. And in the very, very early days, it was a single player type game where all the bad guys were played. The dungeon master was the computer generating the bad guys that were playing. And then you got to decide what the player would do. Am I going to go to the east or the west or the north or the south? Because you would basically, your whole map was a 2-dimensional map just based on the cardinal directions, that kind of stuff. All right. We probably can actually see that one of these other pictures here. Ooh, okay. Oh, that's not a good one. Here we go. Even though this one doesn't show us north, south, east, and west, notice here it says here are the exits that are in the current room, and there's an exit called inside, I guess, but typically it would be like a north, south, east, west as you're traversing the town, taking things. And what's funny is when you're looking at this, it just kind of looks like a wall of text to you right now, right? And you can kind of look at it and pick out stuff, although the Waldo guy he had this figured out before he even brought it up on the screen. But in general, what ends up happening is, and human beings are amazing problem solvers, is your eyes get used to the parts of the screen that certain things sit on, and it ends up being that you can go really in real time, and you see where the exits are in the individual room when you pick out the description. You're standing outside a tavern. It's raining. It shows you what other players are here. Ben is there. And then what exits are around, yada, yada, yada. All right. So you would actually get used to picking out the portions of the text that were important. So when you played the game, all those the wall of text kind of almost disappeared on you. Then you had MUD clients, kind of like we have web browsers for browsing the web. You had clients that played that did this, and they would actually help you build up color code the exits so they stood out more, or give you a digital map up in the right-hand corner as the computer's got graphical user interfaces and stuff like that, so you can kind of see where you've been and that kind of stuff. Yeah, those were the cool days. But in any case, so we're going to try to make one of these guys. All right. And we want to think about this from the perspective of what are the parts that make this up? We want to start thinking about this in an object-oriented manner. So we're going to make our MUD, or multi-user dungeon. Well, we're in our game, we're obviously going to have players, right? Now, in the real world today, once the internet was a thing, or at the very least, before the internet was a thing, we had the precursors to it, these bulletin board systems. There was a famous one called Prodigy. Anybody ever heard of Prodigy? American Online? Oy. American Online was like the Nike of the day. Big deal. American AOL. I think it's still around today, actually. I think they own, they might actually be the owners of Firefox now. Was Netscape, then Mozilla, then Firefox, and I think AOL is still around as a company doing something. But in any case, you would use dial-up modems to dial into like a bank of computers somewhere, so you could play online with the other people that were dialed into that same bank of computers, as opposed to today where you have the whole internet, right? All right, but we're going to do a single player version of this, so we don't have to get into network programming in here. You'll deal with network programming in a different class. But in any case, we're going to have our player. We are probably also going to have monsters, right? Because we got to have something to fight. These games were very much about killing bad guys. Okay, except back then it wasn't about like today a lot of our stuff is like modern war type stuff, right? Yeah, back then you were killing orcs and giants and very medieval fantasy type of settings. So players will have monsters. So these are kind of the things that inhabit our world. We're going to have rooms, and rooms are we're going to imagine this as being rooms linked together. So we have a center room here. You can go north to this room, you can go south to this room, you can go west to this room, you can go east to this room, so on and so forth. So we'll build out a map of all these rooms that are interconnected, and then allow our player to say, okay, I want to go to the east, and I want to go to the north, and things like that, and arrive in different places in our map. Make some sense? All right, so we're going to start building this next class. We're going to start creating these, some of these classes. We're going to use this to introduce the idea of inheritance. And we're going to write an old school video gamey type thing in here and give you some really depressing assignments over it that are going to take just hours, so much time. So, all right, I'll see everybody on Thursday.